Hello, are we supposed to be hearing something here?
We're
Just
going to
made an
start in a
announcement
few
there
minutes.
at 7 p.m. So just bear with us. We're starting in a couple of minutes.
Didn't chat. So
Right, I see one person just waiting to be admitted, and then we'll begin. I think we have one or two people still trying to get in. But let's not wait any longer. We've come up to 5 past. So I think we'll begin. Let me just start the recording.
Can't hear you, Davis.
Is it just quiet or? Right, how's the sound quality now, Mick? Can you hear us okay? We're having a problem with the sound, yeah?
You
I can
sound
hear you
okay
fine,
to
Dave.
me, Dave.
Sound okay, okay. What I'll do, I'll shout. I'm good at that.
No,
No,
you sound.
can hear
you
you
sound
fine.
perfect.
Sound fine, okay, great. Right, well, we'll get everyone to turn off their video, except maybe myself and Rosa, our speaker. And let's begin. Let me start the recording again. Well, good evening, ladies and gentlemen, and welcome to this November meeting of Astronomy Ireland. I'm David Moore, the chairman of the club and the editor of our magazine. And tonight we're delighted to have Dr. Rosa Santamaria, who's come all the way from Italy via Edinburgh, the US, and NASA to tell us all about microbes in space. So I'll do a formal introduction in a moment, but what we always like to do at the beginning is just tell you about what's been happening in astronomy in Ireland since our last lecture, which was another NASA speaker. I'll tell you about that in just a second. But before that, I know some of you are new to Astronomy Ireland, so a brief bit about what we do. We have these monthly lectures where we'll have some brief introductions about what's been happening in the past month. Then we'll have our main speaker. Then after that, we'll tell you about what's coming up in the future. That'll only be a few minutes, the big story for the future. is the eclipse of the moon that's coming up this month. So do stay on after our speaker for that. And then we'll tell you about our Christmas lecture that's also coming up in the next month. So that's a bit about what we're going to do, past, present, and future. We'd like to welcome all of our members from all around the 32 counties. I've seen people logging in from as far or signing up for tickets from as far away as Donegal, which is fantastic to see. Something Zoom allows us to do that we couldn't do in the past. The society has been booming in the last year. It was our 30th year when the lockdowns all began. And in fact, our membership doubled because people are going back to their hobby. More people joining a day than used to join in a month, which was fantastic to see. So the society is really booming at the moment, record membership. So what do? Well, we produce our monthly magazine called Astronomy Ireland, of course. Hopefully some of you are members and all get that every month. It tells you what to see in the sky, what people have been seeing, and all the news from around the universe. We also have a weekly email that's only sent out to members. We need more information on it and reminders of things that are coming up. These lectures, of course, which you can get the last one online, usually for about a month. And then you can get lectures going back decades on DVD. So have a look at our website if you want a list of those. We've had speakers from astronomer royals to Professor Brian Cox, the BBC's rock star astronomer, and all points in between. The other thing we do, our evening classes, they run twice a year. They're currently running, which you can actually enroll now. They're on every Tuesday, and they'll be repeated in February. So you can repeat even the classes you've already seen. In fact, you'll be getting 1.5 sets of classes if you sign up now. So at any stage, go to astronomy.ie, our website, click on events. You'll see the evening classes in there and sign up. If you sign up for next February's classes, we'll put you on the list for I think it's 4 more. There's still to go, 4 out of 8 before Christmas. So you'll be able to enjoy them twice if you wish. So enroll now and tell your friends. Great gift for Christmas as well, by the way. Very popular every Christmas, especially last Christmas under all these lockdowns we had. We used to run lots of watches with telescopes to show the moon, planets, and eclipses. Obviously, they've stopped in the last 18 months, but we're chomping at the bit to get those back running again. That'll probably be a year before all that happens again. We can have a big crowd. We've had 1,000 people outside our offices in Blanchardstown trying to look through our telescopes. So more of those in the future, but something we're very proud to do and which we always enjoy doing. But one event we did manage to run was just a weekend before last, which was the Starbq, Ireland's biggest annual star party. It's held in the Wicklow Mountains, where the skies are extremely dark. I could see the Milky Way, as usual. And we have an array of telescopes spread across the pitch, a professionally catered barbecue, 3 fantastic talks about the universe and black holes and the James Webb Space Telescope. You can actually get those online and on our DVD page still if you missed it. And a fantastic rocket launch by the Irish Rocket Society. And lots of exhibitors too. A brilliant evening. If you missed it, well, don't worry. The next one's on the 27th of August, 2022. And some people have already booked it. You can book that at astronomy.ie. One thing about the Starbq, there'll be a big report in the next magazine, but we were still a little bit restricted by COVID in that a lot of our volunteers couldn't make it and we didn't have an official photographer. So we only got a few pictures and we want to get more pictures into the magazine for a report because it was a huge Starbq, one of the biggest crowds we've ever had. 300 or 400 people, I think, were there. And if you took a picture at the event, please send it in, magazine@astronomy.ie. And hopefully you'll see it in the next issue of the magazine. To do that after the lecture, if you took any pictures at all, we'd appreciate, pictures of crowds, telescopes, anything at all, just to give people an idea what it was like to be there. You also do talks in schools. In fact, this is National Science Week this week. And this lecture is part of the Science Week talks that we always have a lecture in November, at the beginning of November anyway. And we are actually speaking in Gorey Library, I think on Wednesday, and Arklow Library on Thursday. Another talk on Zoom on the Friday. So we're keeping busy as well. And we've been talking in schools last month, sometimes online, sometimes in person. And we'll do it again next month if you invite us anywhere in Ireland, any of the 32 counties. We also keep a huge media presence because Astronomy Ireland is the world's most popular astronomy club. And that's because we try to engage the general public through the media. So you might have seen us on TV, radio. You'll see on our social media lots of posts about that when we're doing an interview live, usually about some currently interesting topic. We're always looking for volunteers to help do all this. We're a very busy Astronomy Society with thousands of members around the country and around 100,000 following us on social media and the like. So that keeps us very busy every day, I can tell you. Social media is free. It's where you'll find space station predictions, aurora predictions, and things like that. So that's a bit about what Astronomy Ireland does. I hope you'll join. Astronomy.ie, see a big join banner there. Just click on it. Anyone can join. You don't need a telescope or any knowledge of astronomy. So what's been happening since the last lecture? The last lecture was a little bit unusual. They normally happen on the second Monday of the month, all year round. But our speaker, George Tahu, who's NASA's Mars program executive, is a very busy man. And so we were able to accommodate him on Thursday, October the 7th, to give his talk about the Perseverance rover. And this is the man who's responsible for all these missions. So this was the top level. If you're interested in the exploration of Mars, do check that talk out. Still book it and see the recordings of it online. It's probably on our YouTube channel as well. So that was a fantastic talk. So big thanks to George for taking the time out of his busy schedule to talk to Astronomy Ireland. I mentioned the evening classes are running every Tuesday. Roll for those anytime online. We also celebrated with NASA again, a bit of NASA theme running this evening, that it was International Observe the Moon Night after George's talk in the middle of October. And we couldn't hold a physical watch, so we encouraged everybody in the country to go out and watch the moon. Some had clear skies, some didn't. The other thing that's been happening in the sky is that after last month's talk, Venus, Jupiter, and Saturn were all near the moon. And Venus repeated that last night and tonight. I hope you got to see it tonight. I was watching it last night. It was an absolutely spectacular sight to the naked eye, with the moon hanging there, a beautiful crescent in the twilight sky, Venus blazing next to it. Got some nice snaps myself. If you've even got a camera on your phone, you would have got a brilliant photo of it tonight. And I would urge you, if you're watching that, you took a snap, do send it in to magazine@astronomy.ie. The other thing we were watching, not in the evening sky, but if you like getting up at the crack of dawn, and I know you all do, was the International Space Station, which was blazing over. In fact, tomorrow morning is the last chance to see it in morning skies. It'll be very low down, though. It's last pass that technically is visible. But it'll be back in the evening sky starting November 19th, the night of the eclipse of the moon. So November 19th is going to be a very busy day. So watch out for the daily predictions of that on our social media. By the way, links to our social media are on the website, astronomy.ie. Click on Facebook, Twitter, or Instagram, whichever is your favorite. We last week had an aurora alert. Now, we've had several, and they failed to materialize. When there are explosions on the sun, we can usually get a 2-day warning that they might hit the Earth. It's not always a guarantee, and I was beginning to get a bit jaded sending out these alerts and then nothing much happening. But fortunately, the universe cooperated last Wednesday night. There was a superb aurora. We got pictures from Ireland. Some parts were clear. There was lots of reports all around the world. We want the Irish photographs. If there's any chance you took a photograph and you haven't yet sent it in to magazine@astronomy.ie, please do so tonight after the lecture, because we're putting the next issue of the magazine together at the end of this week. So we're doing it at the moment. And if you missed it or get the magazine, you'll see that report at the end of next week. It should be in your letterboxes magazine. So we've had a very busy last month, from our NASA speaker to another NASA speaker. I'm going to tell you about the eclipse of the moon coming up on Friday week. So do stay tuned for that. But now we're ready for our main event of the evening. Firstly, about questions. We're going to invite you at the end just to unmute your speaker and ask your question directly of Dr. Santamaria. So don't ask questions during the talk, so we can move along fairly quickly and save them up for the end. You can jot them down or whatever. Okay, so our main speaker, we are delighted to have Dr. Rosa Santamaria, who has worked at NASA. She's now a researcher in space, microbiology and astrobiology at the University of Edinburgh. She studies how microbes react and behave in space conditions and how to use this knowledge to support human space exploration and its sustainability. During her research, she performed 2 biology experiments on board the International Space Station, the Byrock in 2019 and Bioasteroid in 2020 and this year, 2021. The focus of our future research will be on waste recycling in space. During her research, she's worked at NASA, Stanford University in California, universities in France, Mexico. She was telling me earlier she's originally from Italy, and she currently collaborates with the European Space Agency and the Italian Space Agency as well. So I'm delighted to ask her to give her talk this evening, Microbes in Space, How Bugs Help Us Understand the Cosmos. Over to you, Rosa.
Thank you very much, David. In the meantime, I forgot to charge my laptop, so you saw me moving around because I was, oh my God, the charger. But now it's done. Okay, so thank you very much for having me here tonight. I'm very happy and excited, and thank you for the invitation. I hope you will like my topic because it's about microbes, basically microbes in space, but basically microbes. So maybe something that is not, I don't know how familiar you are with that, but don't worry, we'll try and get through that quite slowly. So let's go to I'll share my screen. And I'll pick my pointer. Okay, so tonight we are going to talk about microbes in space, or in other words, how bugs helps us understand the cosmos. I don't have to introduce myself because of the kind introduction that you made, so thank you for that. I'm just going to say that at the moment I work at the University of Edinburgh, so I'm not very far away from you, close by here in the UK, unfortunately not in Europe, but that's another story. So what are we going to talk about today? The first thing is that we are going to define what a bug is. Now, when I moved here in UK, I learned that when they teach us what a bug is, we think about a bug like an insect. But here, when you say bug, you always talk about microbes as well. So in this context, tonight I'm going to talk about microorganisms in particular. And I'm going to explain how and why to study microorganisms in space, or why we want to do that. And I'm going to show you some of the possible applications of microorganisms in space. I will focus on 2 main applications that are linked to my work, which are in situ resource utilization and space biomining. And regarding this, I'm going to talk about the 2 space microbiology experiments that I performed on board the International Space Station so far, and then something about the future of space microbiology, and then I will leave you with some useful links at the end. So first things first, what is a microorganism? So when we say bug, or more accurately microorganisms, what are we talking about? Now, this is a graphic representation of what we biologists use to define basically all the different organisms, living organisms that we know. This is called the evolutionary tree of life. Of course, as I say, this is just a graphic representation, but it is quite nice because it helps understanding a little bit how does it work. So as you can see here, every branch is a different group of organisms. Now, for instance, we are here in the branch of the mammals, which is the branch of the vertebrates, and we are in the branch of the animals. Then there are fungi here, plants, and so on. Now, when we talk about microorganisms, we are normally referring to these branches here. The branch of the archaea, the branch of the bacteria, which are probably the most familiar ones, the protists, and also fungi or fungi. I never know how to pronounce this, particularly unicellular one. In fact, microorganisms are very diverse. There are different types of microorganisms. You can see unicellular algae, you can see archaea, bacteria again, unicellular fungi, like for instance, molds, viruses. We are very familiar with viruses nowadays, unfortunately, or for instance, protozoa like amoeba. So as you can see here, they are very different, quite diverse one to each other. However, there are some characteristics that are in common among them. For instance, the first characteristic that they all have is that they are extremely small. This is why microorganisms. Micro comes from micrometers, which is 0.001 millimeters. They are all quite small organisms. The second characteristic is that they are single cell organisms, or even less, like in the case of viruses. Viruses, in fact, are not made of cells. So they are called unicellular microorganisms. And this made them quite simple. And so this comes to the third characteristic that they have in common, which is that they have been found basically everywhere on Earth's biosphere. Everywhere we search for them, almost everywhere we search for them on Earth's biosphere, we found them. Why does this come from this? Because the fact that they are quite simple makes them very versatile. They can adapt to a large amount of different conditions that would be very uncomfortable for us. So, for instance, when I say that they have been found everywhere on Earth's biosphere, I mean it. For instance, they have been found on soil or on rock environments. They have been found in structures. Like here, for instance, you can see just a pipe full of biofilm, which is a structure that is formed by microorganisms. You can find them in very, very hot environments. This is, for instance, a hot spring. You can find them in very dry environment, like for instance, the desert, in high altitude, like clouds, in very salty environments. This is an image of the Dead Sea, in very cold environments, and last but not least, also in our own body, so in plants, animals, and we are animals, so also on our own body. Now, when you think about which is the harshest environment possible, possibly because you are all passionate about astronomy, we could agree on the answer to that. To me, the harshest environment that I can think about is space. But why is that? What do I mean when I say that that space is such an harsh environment from the biological point of view? Let's see which are the conditions that are relevant from this point of view. But before doing that, we have to define space. Now we got to a place in which you are probably more expert than me, because I have a background in microbiology, so I know a lot about biology but less about astronomy. However, the definition of space is basically the space is defined starting from the Kármán line. You are probably familiar with this. So all outer space is defined at the altitude above 100 kilometers above the sea level on Earth. From here on, we are in outer space. From here below, we are not in outer space. In fact, you can see, for instance, commercial aircraft, meteors, and so on. While here in outer space, we can see the aurora, we can see the former space shuttle, the International Space Station, satellites, and so on. Now, why am I talking about that? Let's get to an image which shows exactly the same, but in a more accurate scale. So if this is Earth here, you can see this part. I zoomed in because it's quite small to see here. So if you zoom here, you can see that this little ball here is Earth. And here you can see troposphere, stratosphere, mesosphere. So exactly the other image upside down. Here we have the Kármán line. And this image here is just for me to introduce this acronym here, which is LEO, standing for Low Earth Orbit, because I'm going to mention this a lot in the next slide. What is the low Earth orbit? Well, it's the orbit in which the majority of space stations, spacecraft, space shuttles orbits, basically. Included, as I mentioned already, the International Space Station. So remember LEO. And then just a curiosity, no human except for the 24 astronauts who have visited the moon has ever ventured beyond this point. So this makes everything in perspective, like our own humanity in perspective. Makes me think a lot about how small we are, but that's philosophy. Now, I was saying that space is a very harsh environment from the biological point of view. But why is that? To answer this question, I have to show you which are the conditions that are present in space from the biological perspective. So the first condition is definitely vacuum. What is it? Vacuum is the condition of absence of matter or extreme low pressure. In Leo, see the acronym that I said before, vacuum goes from 10 to the power of -7 to 10 to the power of -4 Pascal, more or less. In this condition, from the biological perspective, an organism will experience two main effects. The first is desiccation, due to the fact that the water will basically evaporate from the cell surface or also from the surface of the body. And also asphyxiation because of the absence of matter, so also absence of oxygen. These are the main two bad things that will happen to living organisms in vacuum. This is just to show you that in many sci-fi movies, you can see that when astronauts remove the helmet by accident, the eyes explodes, the face explodes, the body enlarges or something like that. This is not really accurate, and I may say that actually sci-fi movies are getting more and more accurate over time. However, you will still die in a matter of seconds, maybe 1 minute or so, so it's something that you don't want to experience. The second condition, which is relevant from a biological perspective, is temperatures. In fact, when we are in deep space, the temperatures are very extreme. They can get to as close as almost the absolute zero to 10 billion Celsius degrees, so very extreme, very low and very high. However, when we refer to Leo, for instance, the temperatures are still extreme, but they depend mainly on the position of the spacecraft in respect to the sun. So when the ISS, for instance, is here closer to the sun, the temperature is around 121 degrees. When they are on the other side, the temperature is minus 157 degrees, which is still quite harsh. We could not survive really in these temperatures, but of course less extreme than the temperatures present in deep space. The other condition is radiations, is probably the first one that we think about when we think about harsh conditions in space. Which radiation are present in deep space? Well, we have definitely galactic cosmic radiation, solar cosmic radiation, banal radiation belts, and the solar electromagnetic radiation, like for instance, the UV radiations. But why are they bad from the biological perspective? Well, it's because of the fact that they are high energy. So all the energy can directly or indirectly affect the molecules, the biological molecules that are in our body or in a microorganism. And this energy can cause direct or indirect damages, which can lead to either mutation or cell death. So very bad, basically. It's due to the high energy that is transported with the radiations. And then last but not least, in space, we have different gravity conditions. In this moment, I'm just going to mention microgravity, which is the gravity condition which is present particularly in spacecraft orbiting around Earth. So as you know, the gravity acceleration on Earth's surface is 1g or 9.81 meters per second squares. When we are orbiting around Earth, for instance, in Leo, the force of gravity is not removed. In fact, when we say zero gravity or absence of gravity, this is not really scientifically accurate because gravity is never removed. However, an object which is orbiting in Leo experience a constant state of gravity-induced free fall around Earth. And this is a state that is referred to as either weightless or more accurately microgravity. Microgravity is normally a gravity condition which is less than 0.01 g or 10 to the power minus 2 g. So this is the reason why we see images like that, astronauts floating around, objects on the ISS floating around. It's because they are in these free fall. However, I want to mention just very briefly that this is the condition of space, open space, etc. But when we refer to, for instance, the moon or Mars, we still have different gravity conditions. For instance, on the moon, we have a gravity condition of 0.16 g. On Mars, we have 0.38 G. So still in space, we have to consider that we have gravity conditions that are different than those on Earth, and this could influence some applications, some type of science that we want to perform in space. Now, let's go back to the microorganisms. I mentioned what a microorganism here. We talk about what space is and also from the biological perspective. So why do we want to study microorganisms in space? From my perspective, as a space microbiologist, of course, the answer is yeah, because it's very cool, it's fantastic. However, if I have to explain to you why it is important to study microorganisms in space, I will definitely split the question in two. So why microorganisms and why in space, although you will see the answers are linked one to each other. For instance, we've seen that microorganisms can survive the harshest environment, and we've seen how extreme the conditions are in space. This can actually tell us, to study microorganisms in space can actually tell us something about the boundaries of life, something about early life, the origins of life, also about possible extraterrestrial life. So this is one of a main topic in astrobiology, which is the field that I study. Some microorganisms are very good models from other type of biology research. And also there are some problems related to health. For instance, it has been seen that microorganisms have a higher resistance to antibiotics in space. So this has important implication for human health. For instance, the health of the astronauts in space. They can also be important for the production of drugs and vaccinations, vaccines, and also for other applications that I'm going to mention in a minute. And it is also they are also going to be essential to create habitable extraterrestrial environments. But I'm going to talk about this in a moment. They are also relatively cheaper in respect to other type of experiments. And why do we want to study them in space? Well, some of the space conditions that we want to test are not reproducible on Earth. So we to have the best science possible, to have the best answers possible, we have to go in space directly and test the determined conditions. They are also very important to study to understand the possibility of human space exploration, and also just for the sake of knowledge, because it's very, very nice. It's beautiful to study microorganisms in space. However, there is one reason which is probably, I don't know if it's the most important one, but it's definitely one of the most relevant one. And it's that, if you remember, I told you that microorganisms are everywhere. They have been found everywhere. And when I say everywhere, I include our own human body. So this means that it doesn't matter where we will go. Wherever we will go in space, we are going to bring our microorganisms with us. So it is very important to understand how they behave in space in order to understand how they could be useful for us and not a threat. And this concept is very important, I think. When we think about microorganisms, we think about very often something which is nasty. I cannot remember how many cleaning products, like advertisement of cleaning products I've seen, in which they aim to eliminate all the microorganisms, all the bugs and something like that. And of course, we are in a pandemic, so I can understand that microorganisms are not seen as something which is very welcome. However, the majority of time, microorganisms are actually essential fellows for us. They perform a lot of different tasks that are essential for our own survival and for ecosystems themselves. Just to mention, oh, sorry, the slide is in Italian for some reason, but it just says they are everywhere on Earth's biosphere. And I mentioned already that they are present in our own body, but only they are present, but they are absolutely essential for our health. In fact, it has been estimated that in a human body, there is a ratio of one bacterial cell for every human cell that composes our body. So we're basically, we can cool say in a very, not not a really scientific way, we could say that we are half made of microorganisms. And they are also absolutely important for our own health. For instance, the microbiome of our guts is very important for our health. Now, I just want to mention, I want to convince you a little bit more about how important, how essential they are for us. And in order to do that, I want to mention some of the roles that microorganisms perform in our everyday life here on Earth. For instance, they were important, they were necessary for the production of oxygen that is currently present in our atmosphere. Around 2.3 billion years ago, before actually 2.3 billion years ago, the early Earth atmosphere didn't have the same oxygen composition of now, but 2.3 billion years ago, the event called Great Oxidation Event occurred, and this was due to the massive production of oxygen mediated by some microorganisms. So we have to thank microorganisms basically for the fact that we have oxygen and that we can breathe today. But microorganisms are also useful for a variety of industries, like for instance, food industry, biopolymer industries, biofuel, and last but not least, also pharmaceutical industries. You may be aware that a lot of drugs are nowadays produced by microorganisms, like for instance, vaccines, but also insulin and others. They are also quite important for the fertilization of soils. So the fact that soils are fertile is also thanks to microorganisms, which enrich soils with elements and nutrients. From an environmental perspective, microorganisms are necessary, for instance, for the recycling process, for the recycling of waste, not just organic waste, but also plastic degradation as well as electronic waste recycling. And also there is a technique which is called bioremediation. This technique is quite an interesting one. Basically, microorganisms are used to decontaminate polluted environments. And last but not least, this is just another technique which is useful for me to explain later on. Is useful for me to mention this now because it's going to be important to explain what the experiment that I performed. There is a particular technique called biomining that uses microorganisms to extract elements from rocks. Basically, I'll talk about this later on. Now, considering how important, how many roles microorganisms perform for us here on Earth, imagine how necessary, how important they could be beyond Earth, for instance, on an extraterrestrial settlement. And just to mention a few possible roles of microorganisms beyond Earth, I thought about some of them, and some of them could be, for instance, in the generation of food. We've seen that they are important on Earth from the perspective in the food industry. So this will be probably applicable on extraterrestrial settlements. For the generation of oxygen, we've seen how important they were on early Earth, so we can imagine that they will be important also on a planetary body. In the recycling of waste, this is something that I'm really passionate about because we've seen that microorganisms are widely used on terrestrial application for the recycling of waste. Now, when we talk about space environment, a space settlement, but even just a space station, as you know, the recycling is very important because a spacecraft, for instance, but also an early space settlement is a closed environment necessary. So the recycling is going to be important because the resources are limited. And for instance, if you think about that, the water is constantly recycled on board the International Space Station. Air is constantly recycled in the sense that it's filtered and cleaned. So recycling on an International Space Station, on a spacecraft, on an extraterrestrial settlement is going to be extremely important for the survival of the settlement itself, but also from environmental issue to be sustainable, for the sustainability of the settlement. And microorganisms can really help from this point of view. Then Microorganisms could also help producing fertile soil, starting from extraterrestrial rocks and extraterrestrial regolith. And this in turn would be, of course, important for the generation of food. And last but not least, when the settlement is going to be fully settled and productive and active, etc., then we can advance our civilization there. And at that point, we are going to need extraterrestrial bioindustries, and microorganisms are going to be quite important from this perspective. Now, all the possible roles that I mentioned here, these are just some ideas, have all the final aim to support them, to sustain what is called the life support systems, so extraterrestrial life support systems. And this is strictly related to the concept of in situ resource utilization, which I mentioned in the introduction. So what is in situ resource utilization? Well, it is basically the use, it is a concept which aims to use the resources in the place in which we are going to settle, rather than relying on a constant resupply from Earth. And this is quite important because this is just an image, a beautiful image from NASA. The majority of space agencies agree that the future of space exploration, of human space exploration, is moving farther and farther from Earth. In fact, the future is to going on the moon first, settle there, and then in future going to Mars. So again, we are going far and far from Earth. Now, from the perspective of the farther we will go, basically from Earth, the less we can think about relying on a constant resupply from Earth, right? Because it's not going to be sustainable, not in terms of expenses. It's been estimated that I think to bring in space 1 kilo of any material, it costs something like, I may be wrong, but something like $100,000, something like that. So we cannot think of bringing everything from Earth and bringing that in space. But also from a sustainability perspective, it's not going to be sustainable. So it is important to learn how to utilize the resources in the place in which we are going to settle, and not taking everything from Earth. From this perspective, the idea, the possibility of performing space biomining is rising and increasing interest. And it is quite maybe obvious to understand why. But before talking about that, let's talk about what is biomining in particular, and more specifically. Biomining, which I mentioned before, is one of the roles that microorganisms perform for us here on Earth. And it is the process of using microorganisms to extract metals of economic interest from rock ores or mine waste. It may sound like a sci-fi thing, but actually is a reality. In fact, around 20-25% of copper, 5% of gold, and also other elements such as nickel, cobalt, uranium, rare elements, zinc, and so on, are currently extracted on Earth using this technique rather than traditional mining. And these are just an image showing some of the molecular processes of biomining, but I'm not going to the details of that. This is maybe the only thing that may be of interest for you, is that if this is the metal surface, basically, or the mine surface or the rock surface, you can see that the microbial cell can extract elements from the rock substrate, either by attaching it directly or also by non-contact mechanisms. However, the biochemical mechanisms are quite intricate and complicated and not fully understood because the mechanisms are wide. However, these are similar to the mechanisms of rock weathering and also of bioremediation, which is that technique that I told you before. So they are all interconnected one to each other. Again, I don't want to get into the mechanism, but I want to point out is that there are several advantages of biomining in respect to traditional mining. For instance, it is considered quite complementary to traditional mining techniques because it can really improve the rate of metal recovery from mine waste, mine heaps and dumps. It is also generally quite economic in respect to traditional mining because of the fact that there are quite few requirements. You basically need the microorganisms and the water and some other few nutrients for that. Of course, I'm simplifying the process, but just to make you understand what the process is. And also it is considered a more environmental friendly technique in respect to the additional mining. Now we can maybe understand why the concept of the possibility of performing biomining in space is quite interesting from the in-situ resource utilization perspective. In fact, when we think about the possibility of performing biomining in space, we are normally talking about performing it on the Moon, on Mars, and on asteroids. Why? Well, Moon and Mars, because as I mentioned before, they are basically the future of space exploration. The future of space exploration aims to go on these two planetary bodies. For asteroids, this is quite interesting. Some researchers, some people are interested in understanding how to extract some rich and precious elements from that are present in some type of asteroids. So there is also an interest toward understanding if space biomining on asteroids is possible. However, the conditions in these in space, as we saw before, are different than those on Earth. And just to mention one, gravity, I mentioned this before, gravity conditions on the Moon, Mars, and asteroid are different, is different than the gravity on Earth. On Earth, we have 1G, remember. On the Moon, we have 0.16 G. On Mars, we have 0.38 G. And on asteroids, we have a condition which is microgravity, in some cases centi-gravity, but still all these conditions are basically lower in respect to terrestrial gravity. Now, if you remember, when I was talking about the mechanisms of biomining, I showed you that the mechanisms are dependent on, can be contact mechanisms or non-contact mechanisms. In other words, the cell can attach directly or indirectly attach the rock surface to perform biomining, right? The question is, if we want to understand if if biomining is possible in space, we need to understand if the conditions that are present in space are going to influence the capacity, the biomining capacity of the microorganisms. And in particular, we don't know how does gravity influence the interaction of the microbe with the mineral surface. So it is with this idea, this question in mind, how does gravity influence micromineral interaction, that we basically performed the two first biomining experiments on board the space station. When I say we, I mean our group here in the University of Edinburgh. Professor Charles Coquel is the supervisor of our group, the boss, let's say, of our group. And we performed two main space microbiology experiments on board the International Space Station. The first experiment is Byrock, and was launched on the ISS in 2019. The second one is more recent, it's called BioAsteroid, and was launched in late 2020, early 2021. They both has the main aim of answering this question: how does gravity influence micromineral interaction? And eventually, how these apply to the possibility of performing space biomining. So let's get into the details of that.
The International Space Station will soon
start later. Okay. Let's talk about Byrock first of all. Byrock was first proposed by Professor Coquel in 2008. So 12, 13 years ago. It took 11 years to get in space. It was first proposed to the European Space Agency, and it was funded by the European Space Agency. They found that a very interesting project, something that should be funded, and it was launched on the International Space Station in 2019. And as you can see from the logos, which are the little logos present on the logo, on the main logo, it was a collaboration among different groups, different researchers and students and so on, and was funded by, supported by the European Space Agency and funded by STFC. And
the International Space.
I'm making a mess. This image, this video that I want to show you here, and it's apparently very not wait to start by itself, is a video that was produced by NASA in preparation to the space experiment itself. Because it was produced by NASA in preparation to the experiment, you will hear the guy talking here in this video, talking with the future tense, but this is just because it's the experiment now has been performed and all. However, I think this video is brilliant, it's very beautiful, it explains very well the rationale behind the Byrock experiment. So I want to show you this because he hopefully will clarify better than me everything. So let's go for it.
The International Space Station will soon host some of the smallest miners in the universe, microbes. Microbes growing on the surface of rocks can gradually break them down and extract useful minerals and metals. This is a process called biomining. As we explore space, we are seeking to use biomining to turn rock and regolith into soil for growing plants and food. But before we can use this technique in planetary settlements, we first need to test it in space. On the space station, bioreactors will be placed inside a centrifuge where microbes will grow on rocks in microgravity and simulated Martian gravity. Investigators will examine how 3 types of microbes behave within pieces of basalt and evaluate how well the different microbes extract elements from the rocks. The findings will be compared to ground-based results. We hope to gain insights into how microbes interact with rocks in microgravity and how we might use them in our exploration of deep space.
Subscribe for more space.
I love this video. I always know it by memory now, but I really like it. So let's get a little bit into the details. I hope the video, I think, is quite clear, but I want to give you a little bit more details on that. The first thing that we needed to decide when we decided to perform this experiment was which microorganisms to use. And we needed to select the best ones. And they needed to have some characteristics in common. For instance, they needed to come from natural rock or soil environment, or in some cases also having a demonstrated capacity to extract elements from the rocks. They needed to be desiccation resistant because of the way they were prepared for the launch on the ISS. They needed to be easily studied in the laboratory. Some of these microorganisms, if possible, needed to be already known to survive in space and to thrive in space. Last but not least, they also needed to be safe for the crew, of course, on board the ISS. So considering all these characteristics that they needed to have in common, we selected eventually 3 different bacterial species. I want to highlight bacterial species because you remember at the beginning I told you that microorganisms are of different types. So for this experiment, we only use bacterial species. And which bacterial species we use? We use these 3 unpronounceable microorganisms: Sphingomonas dissecabilis, which was provided by our group here in Edinburgh; Bacillus subtilis, which was provided by the German Aerospace Center; and Cupriavius metallidurans, provided by the SEK CEN in Belgium. And then we needed to select the rock substrate from which we wanted the microorganisms to extract the elements, right? And we decided to go for a natural rock substrate, which is basalt. Now, why did we decide for basalt? There are 2 main reasons. The first is that basalt is quite porous, is a porous material, so it provided a good support for the bacterial colonization because the surface is quite wide. And also because basalt is widely found on the Moon and Mars, so it provided basically a good analog for lunar and Martian rocks. So we selected a rock coming from Iceland, and we cut this rock in small basal slides, as we call it, which were 13-14 millimeters squared and just 2-3 millimeters thick. Then we prepared the samples. How did we do that? We took a single bacterial culture. A bacterial culture is something like this, basically, a medium containing the bacteria, and we inoculated each basal slide with a single species, with a single bacterial species. Here is again how it looked like basically after the inoculation. But importantly, we also had what we call non-biological control. What is a non-biological control? It's a very important control because it's just basically a sterile basal slide. And the sterile basal slide is absolutely necessary because it will tell us, basically, these type of samples are treated exactly as all the other samples, with the exception that they don't have the biology in it. So having these controls allows us to tell us if the observed data that we have are due to the biology or will occur, however, even without the biology. So it basically will sort out which effects are due to the biology or not. After preparing all the samples, we integrated them into the hardware. This hardware is called Biomini Reactor, or BMR, and it was produced by Kaiser Italia specifically for the space experiment, for our Byrock experiment. Here you can see an hardware with two basal slides in it, and here is an empty one. Here you can see another example of the Biomini Reactor inside the external containment. And here is just some images of us. Before David mentioned that I worked at NASA for a while. It was such an amazing experience. And it was basically thanks to this experiment. In fact, we prepared the samples for the launch directly at NASA Kennedy Space Center in Florida. And this is an image of me, Professor Coquel, and Annemiek Waken, which is a PhD student here in our group. This is part of the Byrock team. This is me again, and this is Charles. And here you can see images of us in July 2019. Feels like a life ago. In NASA Kennedy Space Center, preparing the samples. Here you can see Charles handling the samples to the International Space Station facility, processing facility. So we prepared them there and we handled them directly to the ISS processing facility. They were launched on board the International Space Station on the 24th of July 2019 on a SpaceX Commercial Resupply Service 18 mission. Here is me on the launch site. So I was lucky enough to attend the rocket launch, although it was very far. You can see a zoom in here of the image. Here you can see the Dragon reaching the International Space Station, tracking the ISS. And here you can see the astronaut Luca Parmitano, that in that moment was the captain of the crew, of the ISS crew, installing the hardware inside the incubator, which you also saw on the video. This is called the Cubic Incubator, is an incubator from the European Space Agency. And it is quite an interesting incubator. I'm just going to spend 2 minutes on that, actually a few seconds on that, because you can see that there is a circular structure here and some other allocations outside. I will show you in a minute that the samples were subjected to 3 different gravity conditions in space. Now, the samples that are subjected to microgravity were inserted in this external part here, while the other two that I'm going to mention in a minute were basically put into this central circular part. This part is circular because it's basically a small centrifuge. So by centrifugation, we could simulate other gravity. I'll get back to this. These are other images of Luca Parmitano that was taking some pictures of our hardware on board the International Space Station. And I wanted to show you these pictures because it is important to for me to introduce you to these other pictures here. So now the photo session, so the image acquisition that you just saw in the previous slide, were just basically just a photo session. So just Luca Parmitano just took some images of that. But it turns out that it was quite informative and interesting because the images that have been taken revealed some features that were present when they were in space, but not anymore when we collected back the samples on Earth. And these features are, for instance, these aggregates that you can see here in yellow. Some aggregates were present in space, but not anymore when we got the samples back in our hands. And also the gas inclusions, these bubbles that you can see here with blue arrows, were not visible anymore when they get back on Earth. So it turns out that this photo session, at least from a qualitative point of view, were quite interesting. Now, I mentioned before the different gravity conditions that the samples were subjected. I want to say something more about this. I want to get more clear about that. So these are the samples that we prepared, right? They were all, basically we prepared 4 different sets of samples, including triplicates. 3 of these set of samples, you can see here, 1, 2, and 3 of them were launched on board the International Space Station. And each set of samples was subjected to a different gravity condition. So the 3 that were launched on the International Space Station were subject to either microgravity, so they were sitting on the external part of the incubator that I showed you before, or they were subjected to simulated Martian gravity or simulated terrestrial gravity. Now these two, the simulation of this gravity is thanks to that centrifuge, this little centrifuge that was present inside the incubator that I showed you before. Also, we had a 4th set of samples that stayed here on Earth and was basically subjected only to real terrestrial gravity. And these type of samples, we call them ground control, basically. Now, all the samples, regardless of where they were and the gravity condition, they grew in liquid culture, and they were growing in the presence of the basal light for 21 days at 20 degrees. So these were the experimental features of that. So after this period, after roughly 1 month, the samples were launched back on Earth, and this is us very happy because all the experiment was fine, and we happily and successfully retrieved the samples. And this is me analyzing some of the samples at a microscope. But now let's get into the results. I promise it won't be too complicated, at least I hope so. So the first results that we got from the Byrock experiment regarded the final cell concentration that we analyzed by direct cell counting. So basically, after the experiment, we wanted to understand how the bacteria grew. So how the culture went, was the culture happy in all the gravity conditions and so on. We assessed that by this technique called the direct cell counting. And what we found is that there was no significant difference in the final cell concentration between the 3 samples. So basically, there was no difference regardless of the gravity condition. Now, what does it mean from a biological perspective? This is what we microbiology call a microbial growth curve. A microbial growth curve normally goes like that. There is a first phase called the lag phase in which the growth is very slow. And at some point we have an exponential growth. And then at some point we get to a stationary phase in which all the nutrients are finishing. So basically the growth is not anymore exponential, but it stabilizes. Now, because of how the experiment was designed, we don't know what happens during the 21 days of growth. The only thing that we know is the starting point and what happens after at the 21st day, at this final point. This is why I talk about final cell concentration. Now, we know only this. So we don't know how the growth curve went during the 21 days. It could have done like the purple line or as the blue line, could have gone as this light blue line, the orange one. We have no idea what happens. But what we know is what happens at the 21st day, right? Now, the fact that after 21 days, the bacterial culture all reached the same concentration regardless of the gravity condition is a good indication that biotechnological application on Mars, Moon, or other celestial bodies will be possible because they won't be negatively affected by the gravity condition. So basically, the first result that we got from Byrock is that low gravity is likely not going to be a limit to biotechnological application in space. So a good news. However, I made a big deal about biomining. So what did we discover from the point of view of biomining? To mention the results of this, I first have to mention the elements that I focused the analysis of biomining on. For this analysis, we focus on rare earth elements and vanadium. Now, rare earth elements are a type of metals that have an enormous impact in our everyday life. Despite the name, they are quite abundant on Earth, but they are very important in our everyday life because they are present in every single electronic device, even the smallest one. So you can imagine how necessary they will become in a space environment in which we are going to rely on electronic devices even more than now. And regarding vanadium, vanadium is a metal with a strong industrial interest. It is used normally to strengthen in structural material because it strengthens the hardness, the style strength, and resistance of materials. It is used in alloy, basically. So we think that they are both going to be quite important from a space exploration point of view. And where can we find them? Well, we can find them, of course, on Earth, but also on all the planetary bodies of interest from the biomining perspective. So what did we saw? We discovered that one of the 3 bacterial species that we used, Sphingomonas dissecabilis, was able to biomine rare earth elements in all the gravity conditions that we tested. And the 2 bacterial species, Sphingomonas dissecabilis and Bacillus subtilis, were able to biomine vanadium in all the gravity conditions tested. So very good news, because basically this tells us that space biomining is in principle achievable under different range of gravity conditions. And this makes also Byrock, the first demonstration of biomining on a space station. So quite good. Now, because Byrock was so successful, we managed to have a second space biomining experiment on this International Space Station. I mentioned this before. The name is BioAsteroid. And it is, the schematic of this experiment is quite similar to Byrock, but there are some key differences. Like, for instance, the microorganisms that we used. I said before that for Byrock, we use 3 different bacterial species. So they are all microorganisms, but only they are all bacterial species. Now, with BioAsteroid, we decided to expand our knowledge on other type of microorganisms. So we use a bacterium, Sphingomonas dissecabilis, again, which we already used for Byrock, because basically he behaved very well in Byrock, so we decided to use it again. And we also used a fungus, so another type, a unicellular fungus, a mold, basically, another type of microorganisms. We decided to go for Penicillium simplicissimum, which is a mold which has a demonstrated capacity to perform biomining on Earth. And also we used a mix of the 2 because we wanted to see if the mix of the 2 could enhance or hinder the biomining capacity of the single species. And also, very interestingly, we decided to go for a different rock substrate. Now, while for Byrock, we went for an extraterrestrial rock, right, a basalt from Iceland. This time, we decided to biomine real extraterrestrial material, and we decided to go for meteorite, particularly an L-chondrite meteorite. Here you can see the hardware again. This type we didn't use slides, but we used a crushed material, which enhanced basically the surface that the microorganisms could attach. From the point of view of the gravity condition that we tested, BioAsteroid is slightly smaller as an experiment in respect to Byrock, because this time we only had a set of samples launched on the ISS, and they were subjected to microgravity. And we had a ground control again, in which, of course, just true terrestrial gravity was assessed. The experimental conditions are quite similar, 19 days at 20 degrees. Unfortunately, this time, because of the pandemic, we couldn't go through all the process of going to NASA, Florida, and watch the launch, prepare the samples there, etc. We had to do everything in Edinburgh, but it's still quite interesting. So I had to attend the rocket launch, just as all of us, by the computer. And the experiment was launched in December 2020 by the SpaceX Commercial Resupply Service 21 mission. The samples are back. We are already analyzing them, but the results are work in progress. We're working on them. However, I wanted to show you some of the first images that we got from the analysis of them. So I mentioned that the meteorite was crushed. So we had tiny pieces of rocks for our analysis, right? Now we analyzed these pieces of rock under a special microscope called a technique called scanning electron microscopy, or SEM, which provides these beautiful 3D-like images of the rock pieces. And we analyzed the samples like that to see how basically the microorganisms interacted with the rock pieces, the meteorite pieces. Now, the first thing that we saw is that these are non-biology samples, and these were the samples containing the bacteria. In red, we can see that the the rock pieces, which were in contact with the bacteria, developed these beautiful structures here, and you can see these really look like bacterial cells, right? However, we are still analyzing if this is the case, because when we look at the non-biology samples, we can see structures which are quite similar to those that look like that resembles bacterial cells here. So we are now trying to understand with other techniques if these are really bacteria or just some minerals that forms a structure similar to the bacteria. So again, analysis ongoing. From the point of view of the samples that contain the fungus, now the fungus, the molds, normally forms these beautiful, well, it's beautiful for me as a microbiology, but for people that are not microbiologists, these are not very beautiful. If you ever found molds on cheese or on yogurt or any type of food, you may be familiar to that kind of structures. If you look at the structure, this is called mycelium. And if you look at that mycelium under a microscope, what you see is something like that. You can see these filaments, something like that. So what we saw when we observed the samples that contained the fungus under the microscope, we saw this beautiful mycelium forming on the top of the meteorite surface. Again, the analyses are still ongoing, but basically these images here that I just show you are the first images showing microbial growth on a meteorite on the International Space Station. So quite interesting. Quite cool, maybe more than interesting. Now, enough of my research. I promise I'm finishing my slide here, but I want to give you some insight on the possible future of space microbiology. For the sake of time, I just mentioned my experiment, but there is a lot going on regarding space microbiology experiment, and there is a lot yet to be discovered. For instance, we still need to understand more about the genetic, molecular, and biochemical processes that are influenced by spaceflight. Very importantly, we have to understand what happens in the long duration spaceflight, because, you know, to get to Mars, it will take at least 6 months. So even from the point of view of human health, we need to understand what happens, for instance, to our microbiome after 6 months of, remember the gut microbiome after 6 months of space flight, and even more than 6 months. So we really need to get insight into long-term effect of space flight on microorganisms together with human health itself. We need to understand what is the effect of microbial interaction with other organisms, with other rock surfaces. We need to understand more about virulence and drug resistance during spaceflight, and also about the damages caused by radiation. Again, in the long term, this is going to be quite important. We need to learn more about how to harness the power of microorganisms to perform all the beautiful possible roles that I told you before. Those are ideas, but how can we actually do that? There is a lot going on. There is a lot of research from this point of view, but there is lots yet to be understood and discovered. We need to understand how we could use microgravity for space bioindustries, for instance, and last but not least, also how to keep the process of space exploration sustainable thanks to microorganisms. And this is just the last thing that I want to mention, which is quite important to me. Any space microbiology discovery that we make is going to be important also from terrestrial applications. Just to mention one that is directly relevant for my research, we discovered that one bacteria was particularly important in, particularly good in performing biomining. It was the bacterium Swigomonas dissecabilis. Well, it was not known before that it was a good biomining microorganism. So now we could use these microorganisms also for terrestrial application. So this is just to mention that space microbiology, as any type of space science, actually, is not going to be good for space exploration itself, but also for terrestrial applications. And I want to conclude by, of course, thanking all the Byrock and BioAsteroid teams and all the people that are involved in this. And I want to leave you with these useful links. These are just few of them, but you can email me or write me on Twitter if you want to know more about some of them. And I will leave you with these useful links. And of course, I want to thank you very much for the invitation and for your kind attention. I hope I didn't speak too much. So thank you. I'll stop sharing now.
Thank you very much, Rosa. We said we'd have a few minutes for questions. I see one question in chat, but as I was saying earlier, if people want to ask questions, just unmute yourself and introduce yourself and ask your question.
Hello, my name is Sandra, and what struck me most is that when, like astronauts, to go into space in microgravity, their immune systems become quite compromised. Have you been able to investigate why that happens?
So not me in particular, but there are many research on that, and I think, I don't know, I'm not sure they have like, how can I say, it's very complicated to study that, right? Because the effects are multiple. So for instance, one thing that is important for astronauts is to keep active because their musculoskeletal tissues get degrade over time. So and another thing is for instance, their mental health needs to be quite monitored because of course they are in isolation. It's just 6 of them generally. So there are many things. Microbiology, this is actually quite a good point. Actually, I want to thank you for raising this, because from a microbiology perspective, from a space biology perspective, this is quite interesting because it has been demonstrated that some microorganisms, some virulent microorganisms have an increased virulence in space.
Yeah.
And together with this, we have astronauts with an impaired immune system. So the two things together can actually get quite dangerous.
Yes.
And this is also why, one of the reasons why astronauts need to quarantine before going to space, because they have to be sure that they don't get, any disease in space. And I think there are many reasons why this happens, why the immune system is compromised. It's definitely due to the microgravity condition, is due to the radiation, the higher dose of radiation. But again, it's a multifactorial thing. So it's also due to the diet. The diet is very well controlled, of course, but they cannot, the nutrition, I think sorry, I don't know if I'm answering the question because
No, I think so. I think you are. I'm just curious. Is there a possibility that we need gravity for our immune systems to work properly? Probably that would be one theory.
I don't know if it's maybe in the long term it would be advisable. I don't think gravity is the main problem.
Yeah.
I think really again there is but definitely it is one of the problems, especially from I didn't mention this before because I wanted to not to get too much into details, but it has been seen that from a microbiological perspective, microorganisms cannot directly sense gravity.
Okay.
But they can sense it indirectly because of the effects surrounding it. But from macroorganisms, like for instance, humans, plants, etc., gravity is quite important.
Yes.
So it's one of the factors that needs to be taken into account and makes everything very complicated.
Yeah. Thank you for answering my question.
Thank you for the question.
Yes, and the other thing we want to say, people, stay with us because we're going to tell you about the eclipse next week and the comet that's going to be visible to the naked eye, and indeed the Geminid meteor shower, best one of the year, not to mention our Christmas lecture coming up next. So stay with us. We'll take, I think we have two more questions, one from Mick and one from Edward. Mick, do you want to ask your question?
I can read directly.
Sorry.
I think.
Hello.
Oh, sorry.
Yeah, it's actually Anne.
It's Mrs. Mick.
It's yeah. I'm just wondering if you know, we all know that gut bacteria is so important, and you're saying it makes up so much of our bodies. How does it fare in space? Like, how do astronauts does it diminish in space, or and would that affect them?
Yeah, that's very interesting. So the short answer is that there are many studies on that. But when I say many studies, you still have to think about the fact that the number of studies possible is limited because it depends on the number of astronauts, and the number of astronauts are limited. So if you want to study something on Earth, you have possibly 8 billion people to study, right? But when you are studying something related to astronauts, you have a few. I don't even know how many astronauts there have been in space, but I guess less than 100. So you have a limited number of possible people to study, and so of possible microorganisms. Let's say there are a lot of studies related to the gut microbiome of astronauts, and what they've seen is quite is not completely clear, in the sense that the effects varies a lot depending on the experimental condition, the thing that they are checking. For instance, if you check from bacteria, there are more results. If you check for fungi, for instance, yeast, there are less studies on that. And what they've seen so far is that there is kind of an imbalance, not really an imbalance, but more like the composition of some microorganisms increase and some other decrease. But it looks like there is not a direct effect with this is not strictly how can I say, it's not directly correlated with any disease. So basically, yes, we observed changes, but we cannot directly link these changes with any particular disease or impairment or something. There is just some changes related to the space flight, basically.
Okay.
Yeah, and also it is not clear if these impairments, these changes are somehow related to directly related to this, to virulence. It doesn't look like being like that, but again, the studies are limited by the number of samples, which in this case are people.
Okay, thank you.
Right. Well, we might call the formal questions to an end there, but I'm going to make a few quick announcements. Rosa, do you need to go now, or can you hold on a couple of minutes?
I can hold on, no problem.
Yeah, well, I might ask you some more questions. I've got one involving Jeff Bezos and Elon Musk and you, which I'll ask just after I tell people briefly about what's coming up. So thank you very much again, Rosa. But I'll thank you again in just a moment. Anyone has to rush off, you're going to miss the eclipse details. I should turn my video on so I can tell people about this. First of all, everything I'm going to mention is in the magazine. We have Comet Leonard coming. I'll mention that just a second. But let me just turn the video back on and show you. Oh, yeah, there's the magazine. Hopefully a lot of you already have this. If not, you can order it on astronomy.ie. It'll get to you before Friday week if you order it this week. James is watching in, so I'm sure he'll back that up. He'll be posting it out to you. But in it, it tells you about the eclipse. The eclipse is happening Friday week. It's the morning of. Now, the problem is that the eclipse is not ideal from Ireland. It'd be best in the US. So they'll get to see almost the entire moon go into the Earth shadow. It's nearly a total eclipse for them, 97%. What we'll see is, as the sun is rising and the moon is setting, so that's going to be around the 8 o'clock mark, it'll be going into the eclipse, and it's getting deeper and deeper into the Earth shadow as the minutes tick by. Now, when the eclipse begins, when the first bite is taken out of the moon by the Earth shadow, which will be at, let me read my magazine here, at 18 minutes past 7, it'll already be civil twilight. That means only the brightest stars in the sky will be visible. So the sky will actually be quite bright. So then, until moon set, sunrise, which has to be almost exactly the same time, because they're directly opposite each other in the sky by definition during eclipse, that's going to be at a few minutes past 8. So from 7:18 to 8 o'clock, that's probably when you're hopefully going to see something. But the moon will be very low at that stage. Now, I said the partial phase begins at 7:18, but in fact, you can see the darkening of the moon as it approaches the Earth's shadow. Some people say half hour, some I've seen 45 minutes. So I'm recommending people in the article to start viewing at 6:30. The sky will be dark then, the moon will be much higher up, and see if you can see anything at all, and stay watching till 8 o'clock when the moon sets. Now, the rest of it in the magazine, all you need to do is remember to get up early on Friday week, November the 19th. What else is happening in the sky very briefly? Because as I said, it's all in the magazine. Well, the next magazine is going to tell you about a possible naked eye comet called Comet Leonard. It's been brightening up nicely, and it could reach naked eye visibility in early December. So we'll have full details of that in the December magazine in your letterbox again next week. The other thing that's happening is the moon is going near the planets as usual. So the planets on view at the moment are Jupiter, blazing in the south every evening, Saturn just 15 degrees to its right, about 15 times dimmer, but still plainly visible naked eye. And Venus hasn't been great, very low on the southwest horizon, but it's actually going to get better, and its best will be about mid-December, around the time of our Christmas lecture. And then it'll be, we think a lot of people think, is it the Christmas star? And this bright thing coming this Christmas, didn't come last Christmas? Is this the second coming? No, it's Venus. We're pretty sure we know what the star of Bethlehem was. It wasn't Venus, it was actually a conjunction of Jupiter and Saturn, but that's another story. But at least Venus is going to get a little bit better, and then after Christmas, it starts to fade away again. So it's not making a particularly good evening appearance this year, but I could see it easily last night, and that's going to get better over the next few weeks. There's some great sunspots on view. We give out a fantastic link on the spacecraft that photographs the sun, puts public pictures up every hour. Follow that in the members' email. I saw 3 huge groups today. If one of them has a little explosion, there'll be an aurora alert. That'll be on our social media. So watch out for that too. And then just very briefly, it's actually, Wednesday the 10th. Yeah, so that's tomorrow night, isn't it? No, it's not. It's the night after tomorrow night. Saturn will be nearest to the moon. That should be quite spectacular. Thursday night this week, Jupiter, very spectacular, close to the moon. Diagrams in your magazine. If you like picking up Uranus and binoculars, you'll get a chance Thursday week. Details are in your magazine. Then, of course, next week after that, next day, Friday the 19th, we have not only the eclipse of the moon that morning, but the International Space Station starts appearing in evening skies. And when the moon rises, so it'll set her at 8 a.m., then it'll rise about 6 p.m. later that day, and it'll be near the Pleiades star cluster. And the next night, it'll be near Aldebaran and the Hyades star cluster. So that'll be nicely visible to the naked eye. And I like looking at the moon near the Beehive star cluster. It's going to do that on the morning of Thursday, the 25th. Details are in the magazine. And the last thing to tell you about is the best shooting star shower of the year is coming, the Geminid meteor shower. It'll actually be the night of our Christmas lecture. So watch the Christmas lecture and go out and watch the Geminids. been getting better than the Perseids in August. So that should be quite a spectacle to see. Lots happening in December with comets, the Geminids, and Venus at its best. So it's all in the magazine, except for the aurora, which will be on our social media if one does appear. So that's what to see in the sky. A couple of quick announcements for you. If you like watching the sky at night on BBC, it's on next Sunday. Watch out for that. We'll be reminding people that both on social media and on our members' email tomorrow, or Wednesday, sorry. Evening classes are running every Tuesday. Sign up now. You can finish the classes now. They're all self-contained. You don't have to start at the beginning. And then watch the whole course next February free of charge. Our Christmas lecture is our next talk. We always have a very special speaker for our December lecture to make it something special for the Christmas lecture. It's a great astronomer called Ian Ridpath. You've probably seen him on Sky News loads of times. He's been around for decades. He's a writer, broadcaster, and lecturer, brilliant speaker. And he's very kindly agreed to give us a talk on the 13th of December, remember the second Monday of the month usually, called The Stories of the Stars. So at the Starbq, we had a very powerful laser pointing out the constellations and giving you a little bit of the history, the ancient history behind them. Well, he's written books on this subject, and that should be an absolutely fascinating lecture. One to get the whole family around, because it's not going to be too technical, but great stories from mythology and what you can see in the sky as well. You can book that on the website astronomy.ie tonight. So keep checking us on social media, as I say. Any other announcements will come up there of any events in particular. And if you want to get the magazine, single issue, you can have posted to you, astronomy.ie, you'll see it, or you can sign up and get it posted to you every month. So that's all the announcements, unless Laura or Sonia have anything for me that I forgot to say, or even Anne. Just a reminder there, if you've got any photos of the Starbq, please email them to us tonight, and you'll read all about that magazine. So that's the formalities closed. Hopefully, is anybody sending me a message? I think we're great there. Good. No more announcements to make. That's fantastic. I promised Rosa I'd have another question for her, which was, I remember reading about, and this was financial people, business people, not astronomers, saying that they expect the world's first trillionaire, only Jeff Bezos and Elon Musk are only about a fifth of the way there at the moment, to be a space entrepreneur. And one of the ways was mining asteroids. I'm wondering, are you going to be the world's first trillionaire, or is there any interest from industry?
Well, that would be cool. Yeah, sure, it's going to be. With science, it don't make too much fun. I'm at least with research.
You get any interest from business people who are interested in mining this commercially, obviously over decades of time, not straight away, or is it still just an academic pursuit really at the moment?
So there is a lot of interest toward this concept, this possibility of space asteroid biomining. Sorry, asteroid biomining. But what I think is that at the moment it doesn't look to be feasible. Then of course science can surprise everyone, and the technology will develop, and maybe in future it will be feasible. At the moment, it doesn't look to be very sustainable. There is people thinking that, researching the possibility of how to performing basically mining or biomining on asteroids, and then collecting the leachate, which is basically the metals that have been extracted, and taking that back on Earth or on the closest the closest extraterrestrial settlement. For instance, if you need to have useful elements from you, let's say that we are settled on Mars, right? And we need some rich elements. We could go on the asteroid belts and get elements from there, and then collect them on Earth. They say on Mars, take them on Mars. There is people thinking that this could be a possibility. I think at the moment it's not really feasible, but again, who knows, maybe in future will be. So I don't know. This technologies are not there yet.
Yeah, because I thought since you're in Edinburgh and Jeff Bezos in Glasgow, he might be arranging a quick meeting for a few $1 trillion. Well, not to worry. And maybe eventually, get wise to the idea. I think, to be fair, I think it was a Forbes magazine article, and they were suggesting that they would actually tow the asteroid back to Earth orbit and then throw the rocks somehow down onto the
There is
Earth.
another, yeah.
Might be a cheaper way of doing it. We'll see, though. You never know what can happen.
Yeah, in 100 years, 150 years.
Yeah, if anybody else has any questions, please jump in. Just
I have
unmute
a
your
question
speaker.
from Tom, which is, he sent me as a direct message, probably he meant to be from everywhere. And Tom asks, how did you manage to ensure the sterility of the basal samples on the Byrock experiment before application of microorganism cultures? Thanks, that's a good question. So I mentioned when I was talking about the characteristics that helped us to select the right microorganisms, I mentioned that one of the characteristics was that they needed to be resistant to desiccation. So what we've done was that we prepared the samples before the launch, and we prepared them by sterilizing the basal slide, basically just baking them. So we literally put them into an oven at 250 degrees for 4 hours and a half. This allows all the carbon content to not to dissolve, but basically to nothing that we know about can survive such a high temperature for so long. So this would have killed everything into that was present on the basal slides without altering the mineralogy of the rock, basically. And this is how we perform the sterility. Then with these sterile rock samples, we basically took the bacterial culture and we inoculated them on the basal slide in order to make them, to make the experiment start when they were in space and not on Earth. What we've done is that we inoculated the basal slide, the sterile basal slide with the bacterial samples, and then we desiccated the cells on the basal slide. When bacterial cells are desiccated, if they are not desiccation resistant, they will die. But in the case of our samples, they basically get in a dormant state, and they will stay in this dormant state as long as we want. And they will start growing back when the liquid culture, so when the liquid medium, the nutrients are available again. So what happens is that the hardware that I showed you for the Byrock is quite an interesting, quite a beautiful hardware, because it allowed us to put the samples in this dried state, launch them in space, and then at the precise moment, the hardware basically injected the nutrients, the liquid nutrients. They were in contact with the liquid nutrients become in contact with the basal slide containing the bacteria, and so the bacteria was not anymore in a dormant state, and they started growing again. I don't know if I am explaining this correctly, but basically, like,
No,
if it's clear, I explain.
Yeah. No, that's great, Rosa. That really explains it. Thank you so much for such a great lecture. It was absolutely brilliant.
Oh, thank you.
Rosa, Ed Malarkey actually posted a question in chat there. I don't know if you can see it.
No, I don't think so.
I just resent it on. I'll give you, it's very small on my screen. I can just read
Yes.
you got it,
Excellent. Is it? How do we extract the minerals from the microbes, and what about quantities? Good question, this as well. So in our case, so we tested two things. When the samples arrived back, the microorganisms were in this liquid culture. So we separated the rock, the basal slide, from the liquid culture. The rock slides were analyzed for other techniques. The liquid culture contained basically the minerals that have been extracted and the cells. So we separated the two and we analyzed the two separately, so that we could see how many elements were present within the bacterial cell and how many were actually extracted from the rock, but then put them in the liquid fraction, basically. And from this analysis, we discovered that the fraction of elements that were retained within the bacterial cells was very, very low, was less than 5%, while the fraction that was present in the liquid the elements that were present in the liquid was the high majority of the elements. So this means that the bacterial cells of the bacterial samples that we used extract the element and release them in the liquid. So they don't need them for their metabolism, or at least they don't need them in a high amount. Sorry, I'm reading the question again. How do we set the minutes? Okay, so what we've done to analyze them was basically we analyzed them with a technique which is called ICP-MS, which is basically a coupling of two different techniques, very complicated techniques. One is chromatography, and the other one is mass spectrometry. And this is a technique which allows to measure the elements in a very, very low concentration, part per billions, if I'm not wrong. And in future, if you want to do this in an industrial level, there are several. So what we've done at the moment is basic research. So we were not interested in understanding how to do that from an industrial point of view. So we were just interested in understanding, okay, can the bacteria extract the element? Yes, no, how much, etc. But the technique that uses that on Earth basically use several post-processing, which I think they are partially physics and partially chemical, to then take the liquid fraction and collect, precipitate, and concentrate basically the elements from the liquid fraction. So I hope I answered to this. And regarding the quantities, depending, so rare earth elements in particular, they are a range of, I don't want to get wrong, but more than 10 elements. I cannot remember exactly how many elements they are. And the relative quantity of, let's say, the percentage of elements that have been extracted are higher, generally higher, depending. So the trend is that the higher the gravity condition, the more they are extracted. But still, if you confront them from a statistical point of view, there is not really a big difference one to each other. However, we've seen that in some cases, which I don't remember now the precise details, but some of these rare earth elements were extracted like 4 times more from the biology in respect to when the bacterial cells were not present. So the biology is really doing something in this sense. They are really extracting the cells more. So basically the elements are extracted thanks to the microorganisms and not just because of the chemical processes due to the leaching of the liquids or something like that.
That's great, Rosa. I'm just wondering, anybody else want to ask any questions before we let Rosa go? A few seconds to figure out where the unmute button is. We've still got.
Rosa, sorry, Rosa, can I ask you another question? It's Tom here.
Hello, yes.
Why did you choose basalt, and is it possible, because you just used one sample of one rock, that if you'd used limestone and basalt, that you might have got two different results?
Sorry, can you repeat? I don't think I got the question.
You used basalt for your experiments. Why in particular basalt? And could it be a possibility that basalt might have been a better grower of bacteria than limestone would be, say, for instance?
Okay, so we use basalt because basalt is present on the Moon and Mars. So we wanted to get something, something that was kind of an analog of these two planetary bodies. And of course, it must be said that there are some analogs of Martian and lunar regolith. So if you want to be more, if you want to get more insight on for instance, we want to know exactly, not exactly, but like we want to know more on Martian biomining on of Martian rocks. We could use Martian regolith, particularly. If we want to know more about biomining on of lunar rocks, we could use lunar analogs. But basalt is a good analog for both of them because, again, it's a type of rock which is widely present in both planetary bodies. So this is why we decided to go there. I might say I'm not a geologist, so I don't know if limestone are present on the Moon or Mars. My suspect is that it's not present there, but I may be completely wrong.
Yeah, I actually don't know myself, having said that, but I'm pretty sure basalt's being a volcanic rock. It's bound to be present on both bodies, but I don't know about limestone. Thanks, that's a great answer.
Thank you.
Now we're coming quite late. If anyone wants to jump in, one last question, or I'll close the formality. Right. Well, thank you very much indeed, Rosa, for taking your time to talk to us this evening about a fascinating area I knew nothing about. Now I'm going to have to go off and investigate becoming a trillionaire on all this.
I will as well.
Be sure to put you in for a percentage. So thanks everyone for listening in, and a big thank you to Rosa. I know you're coming to Dublin in December. Hope you have a great time. Pity we couldn't meet in person. Maybe again in the future. So thank you everybody indeed. And thanks for everyone who helped put the meeting together this evening.
Thanks.
Bye-bye, everybody.
Bye. Goodbye. Good night, everyone.
Bye-bye.
Thank you. Bye.
Bye-bye.
If anybody wants to stay and ask any general questions about the eclipse or telescopes for Christmas or anything like that, I'll hang on for a few minutes, but we'll let Rosa go. I think she's done a great job this evening. So if you do have any questions about general astronomy, just blast them out.
Yes, I'm going. Thank you again.
Bye, Rosa. Thank you.
Bye-bye.
Anne and I have to go now, David. So
Yeah, you've got a magazine to produce.
yeah, we have another appointment. Actually, we have to go out.
Oh, right. This time
You're going to disappear.
Yeah, go ahead. No problem. I'm just going to hang on for a few seconds in case anybody wants to ask anything. There's only 9 participants left, so.
Thanks a million. Take care.
Bye.
No problem. Now, if we don't hear anything from you in about 5 or 10 seconds, I shall end the meeting altogether. Great. Thanks, Sonia. Thanks, everybody else. I think we can end the meeting now. I've ended the recording anyway. Great. Well, good night, everybody.